Welcome to our discussion on derivatives and what they tell us about the shape of a graph. Now you might be thinking, why should I care about learning techniques to help me graph a function? I can just plug that into a calculator or use some sort of technology and get a graph far more accurately than I could ever draw by hand. And that is true. And as we are going through these techniques, we will always be looking at graphs afterwards as if that were the culmination of our efforts, but that's not the case. We're just using the graph to kind of verify what we're learning by using these techniques. And you really don't do these techniques so that you can graph a function. You do these techniques so that you can find aspects of the graph of the function, like maximums, minimums, inflection points, and where it's concave up and concave down. And again, you might argue, well, can't I just figure all that out from a graph? Well, you can absolutely figure the idea of where it's concave up and where it's concave down and where your inflection points are and where your max and minimums are from the graph, but you can't find the precise values, again, unless you use some sort of technology that will find those for you. But it's nice to be able to find them with the math to make sure that it's correct. For instance, if you're looking at the graph in front of us, you can clearly see that B is a local max and C is a local min, and you can also clearly see that it's concave down from A to somewhere around here, and then it becomes concave up for the rest. But where is somewhere around here? What is that actual x value? And for that case, what is the actual x coordinate of B and C? Those are the things that we can actually find by performing these tests. And both of the tests are just going to require us to take a first and a second derivative and then do some simple work from there. So let's begin with some of the ideas. First, there's the idea of the increasing and decreasing test. And this tells us that if the first derivative is positive on a certain interval, then the function is increasing, and if the first derivative is negative, then the function is decreasing. So go back to this picture and look at what the picture tells us. Can you see how as this function is increasing, all of those red lines have positive slopes? So the derivative, right, which is represented by the slope of the tangent line, is positive on that entire interval. It gets to B, and then of course it would be a zero slope, right? And then as it starts to decrease, these are all negative slopes. And then of course it goes back to zero, and then they become positive slopes again. So we can see very clearly that nice, strong, easy correlation between the sign of the derivative, positive or negative, and whether or not the function itself is increasing or decreasing. Here's an example. If we wanted to figure out where this function was increasing and where it was decreasing, again, yes, I know we could look at the graph, but we can actually find the precise places. So we take the derivative, then we set it equal to 0, because remember, we want to figure out where the first derivative is positive or negative. So if we set it equal to 0, we can test all the places where it's not 0. So of course, to set it equal to 0, you need to factor it, right, and find all of the zeros. So when we factor it, we see that we have 3 zeros. We have a 0 from here, a 2 from here, and a -1 from there. Those are the 3 places where the function equals 0. Now we need to figure out where it's actually greater than or less than 0. And you might recall a similar technique in an algebra or a college algebra or a pre-calculus class that you took, where when you find these zeros, you plot them on the number line and then you use little test points in between each of those to figure out what's happening. And we're going to do the same exact thing here. We're going to take those 3 zeros that we just found, -1, 0, and 2. We're going to write them on the number line, -1, 0, and 2. And the idea now is to just pick an x in each of those 4 intervals, plug it into the derivative, and figure out when the derivative is positive or negative. Now, again, if you have technology that allows you to easily plug numbers into a function, that's going to be the easiest thing. But if you're going to be doing this by hand, and I recommend you do it by hand for the practice, the best thing to do is to leave your function factored. And now you're just plugging those test values into each of those factors. And remember, we don't care what the number is. We just care whether or not the number is positive or negative. So you're really just keeping track of the sign. So for instance, And I'll draw our number line again to help us visualize what's happening here. -1 was our first number, right? Then we had 0, and then we had 2. So we're going to pick our first value here. I'll call it x1. It's going to be somewhere in this interval. It's going to be somewhere smaller than -1. Well, the easiest, quickest thing is just pick -2. When you plug -2 into here, yes, it's -24, but you don't care about that. Just keep track that it's negative. -2 minus 2 is also a negative. -2 plus 1 is negative. When you multiply those three together, you get that the entire thing is negative, and therefore the function is decreasing on that interval. You repeat the process. Pick something between 0 and -1. Now you're stymied. You're like, oh, I can't pick an easy number. I have to pick a fraction. But again, who cares? Because we don't care about the number. We just care about the sign. So even if we do pick -1/2, -1/2 times 12 is still negative. -1/2 minus 2, still negative. -1/2 plus 1, that's now positive. And then the whole thing is positive, right? Negative times negative is positive. Positive times positive is positive. And now we see that it's increasing. We move on to the next one. Well, between 0 and 2, I'd pick 1. Gives me positive, negative, positive, so the whole thing is negative, decreasing. Finally, the last one, something bigger than 2, pick a 3, positive, 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 the whole thing is positive, increasing. Now, please don't think that this pattern will always be true, that it'll always go increasing, decreasing, increasing, decreasing. That's not always the case. You could think about a simple function like x cubed, right? Here, there's going to be a point, if it levels off just right, that you're going to get a horizontal tangent line. You're going to get the derivative equal to 0, but you can see very clearly that it's going to be increasing everywhere. So you're going to get an increasing and an increasing for that kind of function. So just keep that in mind, that it's not always going to alternate. It does happen to alternate a lot, especially since we're going to be dealing with a lot of polynomial functions, and polynomial functions tend to all alternate like that. So you will see this pattern over and over again, but please don't fall into the trap of thinking it is always the case. Okay, so what did that first derivative tell us? Well, it just told us where the function was increasing and decreasing. And because of that, once we start plotting some of the information, we can then figure out where we have maximums and minimums. So we'll go back to this slide. Here's the graph of the function. But even without that graph, we can see that the function was decreasing, right, on this interval. So let's draw these in. It was decreasing here, it was increasing here, decreasing here, and then increasing there. So if the function is coming down in this interval and then popping back up in that interval, doesn't that mean that -1 has to be a minimum? And then if it's increasing and then decreasing, doesn't that tell you this has to be 0, has to be a maximum? And then again, if it's decreasing and then increasing, 2 has to be a local min. So that tells us min, right, max, min, and then all we'd have to do is plug those three values into the original function, right, because remember this is now the graph of the original function, not the derivatives, the original function, and then we'd figure out which of these two is actually the global min, right, and since this is the only maximum we have, it's also the global max, right, local and global, so we could plug it in and figure out what that is, and in fact we see that it's 5. Okay, so we can find minimums and maximums very easily from what's called the first derivative test. And the first derivative test tells us that if we have some critical number c on a continuous function, and we're going to see this over and over again, that these things have to be continuous for this to work. And we've seen all of our previous theorems all are based on the assumption that our functions are continuous. And that's an okay assumption because most functions are continuous, and all the functions we're going to be dealing with are continuous. So it kind of becomes a moot point, but just keep that in mind that it is something that you have to be aware of. Okay, so if we're finding this critical number c on a continuous function, and we have that the first derivative goes from positive to negative, right, and I always like to draw a picture to help me remember, okay, so positive, function's increasing to negative, then we know it's a maximum. But if it's going negative, right, to positive, we can see that that's going to be a minimum. And if it does not change signs, right, so if it goes positive to positive or negative to negative, then it's neither, right? That's where we just have kind of one of those inflection points, and I told you that that will happen. Here's a visual depiction of where we see that maximum, right? There's our positive slope of our tangent line, negative slope of our tangent line, negative slope, positive slope, And then here are a couple examples. Positive slope, 0, positive slope. So there's the inflection point. Negative, 0, negative, another inflection point. All right, let's see if we can put it all together and find the local max and local min of the simple function x plus 2 sine x. And we're going to cut it and only look at it on the interval from 0 to 2 pi. So the first thing we want to do is find critical numbers. And you'll remember from previous lessons that to find the critical numbers, you have to take the derivative, set it equal to 0. So here's our derivative, right? Derivative of x is 1. Derivative of sine is cosine. So we get 2 cosine x plus 1. Set that equal to 0. When you set that equal to 0, you get 0 equals 1 plus 2, cosine x. Negative 1 equals 2 cosine x. Negative 1/2 equals cosine x, right? And then you got to figure out, when does cosine x equal negative 1/2? And if you go back to your unit circle, you know cosine is negative in these two quadrants over here. And if you think about your reference angles, cosine equals 1/2 at pi over 3. So over here it'd be 2 pi over 3, and then 4 pi over 3. And then of course it would keep going, but remember we're only doing one revolution. So those are the two solutions that give us the derivative equal to 0. Now what you want to do is check the function on all of those intervals. Now it might feel weird with these numbers, these things in radians, but remember that's the beauty about radians, is radians are just numbers. So here's 0, right? Here's 2 pi over 3, which is a little bit bigger than 2, right? And here's 4 pi over 3, which is a little bit bigger than 4. Now the 0 is not a critical number. I just put it there to show you where we are on the number line. So the first thing we have to do is pick a number right somewhere in this interval, and we might as well pick 0. Plug 0 into the function. Cosine of 0, remember, is 1. So we get 1 plus 2, that's a positive number. Then we need to pick something in between the two. So 2 pi over 3 and 4 pi over 3, how about we just pick 3 pi over 3, which is just pi. And cosine of pi is negative 1, so you get 1 minus 2. There's your negative. And then you pick something out here, something bigger than 4 pi over 3. How about we go we could go all the way around to here, 3 pi over 2. And that gives us cosine of 0. And 1 plus 0 is positive. So there we have increasing, decreasing, increasing. We know our function is increasing, then it's decreasing, then it's increasing. So we have a maximum here, a minimum here. So we know we're going to have a maximum at 2 pi over 3 and a minimum at 4 pi over 3. And of course, if we graph it, or if we do the math, we can actually figure out what those values are. So we plug 2 pi over 3 into the regular function, right, the original function, not the derivative, but the original function of x plus 2 sine x, and you get roughly 3.83. You do the same thing with 4 pi over 3 and you get 2.46, and you can see that 3.83 is bigger than 2.46. That also kind of corroborates our thoughts that this is a min and this is a max. And if you graph it, you can plainly see that they are your local mins and your local maxes. Now if we were trying to find global mins and maxes on that interval, remember we would have to use the closed interval test thing, where you find the critical values, you test the critical values, but then you also test the endpoints. And you really don't have to worry about doing this first derivative test if you're doing that, because you're really just testing all 4 of those points and seeing which ones are biggest and which ones are smallest. And in fact, you can still use that technique here with the 2 values that you got, but it's also nice to double check it with the derivative. Okay, what is the second derivative? So far we've seen that the first derivative helps us define mins and maxes. What can the second derivative tell us? Well, let's say figure 5 below shows the graphs of two increasing functions. So we've got function f on the left, function g on the right. You can agree that they're both increasing. But the one on the left is concave up. The one on the right is concave down. If you've never heard these phrases concave up and concave down, can you see how this looks like a cave, right? And the cave is facing up. Here's your cave, your cavity, and it's facing down. So there's concave up and concave down. Another way to think about it is if we were to draw our tangent lines on this one, our tangent lines would all have to be below this one, right? And they would all have to be above this one. So the function is below the derivatives, tangent lines, so concave down, and the function is above, up above the derivatives, so concave up. That's another way to help you remember it. And here it is with much better pictures than mine. Concave up, concave down. Okay, so the definition of concavity. If the graph of a function lies above all of its tangent lines on a certain interval, then it's considered concave up on that interval. And if the graph lies below all of its tangent lines on an interval, it's called concave down. So that's literally how we're going to define concavity. But it's pretty easy to figure out just from looking at the graph, right? We can see that from A to B, it's concave down. From B to C, it's concave up. C to D, concave down. D to E, concave up. E to P, also concave up. And then P to Q, concave down. And we're just going to shorten that with CD and CU just because it's a pain in the butt to always say and write concave up and concave down. Okay, so let's take a closer look at how this second derivative can help us determine the intervals of concavity. Well, we can see that as the first derivative is to the function, the second derivative is to the first derivative, right? The first derivative tells us the rate of increase of the function. The second derivative tells us the rate of increase of the first derivative, right? How fast is the first derivative changing is what the second derivative tells us. So in this first picture, you can see that the first derivative, shown here by the red lines, right, because those are the slopes of our tangent lines, starts fairly shallow, pretty close to zero, and then it gets steeper and steeper and steeper. It's increasing. So if we were to take that second derivative, what do you think it's going to be? Positive or negative? And then here, it starts at a fairly steep positive number and starts to level off. It's decreasing. So what do you think about the second derivative? Is it going to be positive or negative? Well, hopefully you're guessing that in this case, because it's increasing, you're going to get that positive second derivative because that's a positive rate of change. It's increasing. And then here, because the first derivatives are decreasing, your second derivative is going to be negative. So, the concavity test. If the second derivative is greater than 0, then the graph is concave up. It's kind of nice and intuitive, right? Positive number, concave up. Second derivative is negative, negative number, concave down. Look at your pictures, right? That's concave down, and the slopes of the tangent line are getting smaller, therefore your second derivative is negative. There's concave up, your tangents are increasing, therefore your second derivative is positive. Okay, this graph here shows a population graph for Cyprian honeybees raised in an apiary. Now, how does the rate of population increase change over time? When is this rate highest? And over what intervals is P, the population, concave up or concave down? So now we have questions that are related to the rate of change, the rate of growth, and not just the actual amount, right? This graph here, this blue line, represents the population of honeybees. If we took the derivative of this function, that would be the rate of change. And we could graph that, and then we could look at its tangent lines, and that would be the second derivative, right? But we can kind of get all of that just from looking at the original graph, because we can see very clearly that we would have a horizontal, right, tangent line, so a slope of 0, and then it starts to get steeper. We're starting to get higher and higher rates of change till we get to about here, and then all of a sudden it starts to level off and the tangents are now above the function. So concave up to about here and then concave down. So it looks like at about 12 is where it starts to change. So what does that mean? Well, can we see that this function is increasing at an increasing rate? It's kind of exponential on this interval. So the first derivative is increasing, therefore the second derivative is positive, and that means the rate of change, because remember the rate of change is the first derivative, the rate of change is increasing. And then here the rate of change is decreasing, right? It's leveling off. Those tangent lines are getting shallower. So it's concave down. The second derivative is negative, and it's growing. It's still growing, right? The population is still getting bigger, but it's growing at a slower rate. It's looking more logarithmic. Well, we can calculate these things by actually taking derivatives and finding these values rather than just looking at a graph and kind of getting a rough idea. By looking at the function, we can see that it seems to level off as far as the rate of change is concerned around 12. Remember we said that it kind of switches from concave up to concave down around 12. And as it approaches that 12, we can calculate the rate of increase. Now this would, we could only do this. These numbers are from actually having the function. We don't have the function, so we can't really calculate it here, but these are the descriptions that we would get from taking those derivatives. Okay, now an inflection point is what we're going to call where the function changes concavity. So that point 12, x equals 12, and specifically the point is 12, 18. Sorry, it's the point is 12 and about what, 45, 50, somewhere around 1,000, right? That would be the actual inflection point. Sometimes you'll want to know x, sometimes you'll want to know x and y. We can find that inflection point because that's where the function changes concavity. It goes from concave up to concave down, or vice versa, concave down to concave up. Well, what do we know about concavity? It's related to the second derivative. We know that it's concave up when the second derivative is positive and concave down when the second derivative is negative. So we can find those inflection points very easily by just taking the second derivative and setting it equal to 0, because we know it's going to be one or the other on each side. Now it doesn't have to be. We could have a function that goes from concave up, levels off, and then goes concave up again, but it would be a very weird looking function. Chances are it's going to become an inflection point. But you always got to check it. You set the derivative equal to 0, and then you check on each side of it, just like we did before with our little test points, to verify that the second derivative is in fact changing signs, going from positive to negative. Here's a simple example. We have the function x squared minus 4x cubed, and we want to figure out its concavity, its points of inflections, its local min, its local max, all those fun things we can do with derivatives. Now remember, I know that you can figure out most of the stuff from a graph, but you can't really find the precise values without doing the math. So we take the first derivative, we factor it, set it equal to 0 so that we can find its critical values, and we get a critical value of 0 and 3. Then we take the second derivative, and I would do it from here, not from here, because then you have to use the product rule. Take that second derivative, set it equal to 0, and again we get two more criticals. It's not always going to be 2 and 2, right? But in this case we get two criticals. Here's 0 and 2. All right, now what do we do with those numbers? Well, the next thing we want to do is figure out what's happening around those numbers. Now we can use the second derivative test to figure out concavity, which will tell us whether the things that we're dealing with are minimums and maximums. So the two critical values we got from the first derivative, if we now plug those into the second derivative, we see that we get 0 and 36. Well, because 0 doesn't tell us anything, we don't know what's happening there. But because 36 is positive, and because positive tells us the function is concave up, that means this has to be a minimum. So we just found that f of 3, and if we plug 3 back in the original function, get negative 27, that's a minimum. Now, as I said before, because the second derivative equals 0, the second derivative test doesn't give us any information about what's happening at 0. So now we have to resort to using the first derivative test and checking for pluses and minuses, right? We go back to drawing our line. Here's 0. What happens on each side of it? We could also, worry about 2 over here, but we really don't care about 2 because we're only concerned with what's happening with 0. So because the first derivative, and in fact if we're going to use the first derivative for our test instead of the second derivative, then we're really thinking about 3 because those were our two critical values. Pick something here, pick something here. Something less than it, figure out what's going on. Something between 0 and 3, figure out what's going on, right? Is the first derivative, or sorry, is the function positive or negative, or is the first derivative positive or negative, to figure out if it's increasing or decreasing. So, sorry, once again, we're going back to the first derivative test here. Pick a value. The first derivative tells us that f does not have a local max or minimum at 0 because if we go back to the first derivative test, and we'll have to remind ourselves of what the first derivative looked like. Right, here it is. 4x squared times x minus 3. 4x squared times x minus 3. Pick something to the left of 0, so pick negative 1. Put negative 1 in here, that's positive, right, because you square it. Put a negative 1 in here, negative and a negative, right, that's negative. The whole thing is going to be negative in this quadrant, right, this part of the number line. Now pick something between 0 and 3, so pick 1. Put a 1 in here, positive. Put a 1 in here, still negative. This is also negative. So now we have from the first derivative test, right, which was the first technique we learned, the function is decreasing on this interval. It gets to 0 and then it decreases again. So our function does something like, sorry, that's a horrible drawing, something like that. And we can see that 0 here is an inflection point, right? It goes from concave up to concave down, but it's not a min or a max. Now we can also figure that out from the second derivative, because remember 0 was a critical point of the second derivative. When we do the second derivative, we now have 0 and 2. And we're now concerned with looking at the second derivative instead of the first derivative. We can use the same test points. Negative 1 gives us a negative here and a negative here, which gives us overall positive. And then between 0 and 2, we can still pick a positive 1, which gives us a positive here and a negative here, and that's where we get a negative there. And then we go to the other side of 2, so we can pick 3. This one's positive, this one's positive. We get an overall positive. So we can see concave up, concave down, concave up. Here's that concave up, concave down that happened at 0, right? And then at 2, it goes from concave down to concave up. So there must be some other inflection point over here somewhere at 2. And in fact, if we look at the graph, there are our two inflection points, right? Concave up to concave down to concave up, and then here's that one minimum that we found from the first derivative test. Now something to pay attention to here is that we were able to figure out what was happening at 0, 0 with the first derivative test a lot easier than the second derivative test. And in fact, it's been my experience that even when you can use both tests, the first and the second derivative, the first derivative test is often the easier one to use. So remember, when we took the second derivative here and it was equal to 0, it didn't tell us anything about that point. Was that point a max or a min? We didn't know, and then we had to go on and do further testing. we could figure out 3 because the second derivative at 3 actually gave us a value, right? It gave us a positive number. We knew it was concave up, and then therefore it was a minimum, and that's great. But we could have gotten all of those answers from just finding the 0 and the 3, doing the first derivative test, which remember is doing the number line and doing your test points and plugging them in, and then we get all of those answers right off the bat. We would see immediately that 0 was an inflection point because it went from decreasing to decreasing, right? And then we could see that 3 was a minimum because it went from decreasing to increasing. So you should always try for the first derivative test. It's the better of the two when it comes to figuring out where minimums and maximums are. Now when it comes to inflection points, that's all about the second derivative test. And that's the easier, usage of it, and it's always going to work. Okay, so our last example here, we can put this all together. And if we're trying to sketch the graph, remember that's not really what we're trying to do. We're trying to find all of these mins and maxes and inflection points. Take the first and second derivatives, pretty ugly things. Okay, with the first derivative, you have 3 pieces, right? You have the top piece and then the product of the 2 pieces. We have, if we set it all equal to 0, we get 3 critical values, right? The top equals to 0 gives us a 4, the bottom equals to 0 gives us a 0 and a 6. So there are our 3 critical values that we want to check. Here's our number line, 0, 4, 6. Pick something over here, so pick a -1, let's say. Plug a -1 in here, 4 minus a -1, that's positive, right? A -1, a cube root of a negative number, it's negative, and then 6 minus a -1, right? That's going to be positive, positive, right? So negative overall, it's decreasing on that interval. Between 0 and 4, I'd pick 1. 4 minus 1 is 3. 1 cubed, right? Positive. 6 minus 1 is 5. That's still positive. The whole thing's positive. It's increasing. So we now know that this function was decreasing to 0, increasing on this interval. We already know this is a minimum. Now we check on the other side of 4. So we check 5. 4 minus 5, negative, right? 5 cubed, that's positive. 6 minus 5, that's positive. So now it's decreasing. Now we know this is a max. On the other side of 6, we take 7. That gives us a negative number, right? 7 is positive. 6 minus 7 is -1, but then we're squaring it, which makes it positive, and then cube rooting it, so we get a positive number here. So the whole thing is negative. That means it's decreasing here, and look, we have an inflection point because it goes from decreasing to decreasing. And we learned all of that from the first derivative test. Much easier and simpler than worrying about taking those things and plugging them into the second derivative. Okay, but this is just summarizing what we already found. Let's move on to the second derivative and figure out what the second derivative tells us. Well, we'll have to remind ourselves what the second derivative was, right? -8 over x to the 4/3 and then 6 minus x. So we still get those same 2 zeros at 0 and 6. All right. So here's our 0 and 6. And we're now dealing with our second derivative. And the second derivative had x to the 4/3 and this one to the 5/3. So we have x to the 4/3 and then the other one is 6 minus x to the 5/3. Now you'll notice anything to the 4/3 is always going to be positive. Right? No matter what we have, this is going to be positive. Because if you take something and raise it to a power of 4, it's going to be positive. Then when you take the cube root of it, it's still going to be positive. This thing here, 5/3, if it's negative, it's negative. If it's positive, it's positive, right? Because when you're raising it to an even power, it keeps its sign. So that's really the only one we have to worry about. Pick a negative number, right? -1. These are all positive. Put a -1 in here. 6 minus a -1 is positive. So this is going to be positive. The whole thing's going to be positive on this interval. Between 0 and 6, pick +1 again. 6 minus 1, still a positive number, still positive. The whole thing is still positive. Something bigger than 6, like a 7, this all of a sudden becomes negative, and this becomes negative. So, we can see that It is concave down So we have concave up on this interval, concave up on this interval, and then concave down on this interval, and this is where our inflection point is. Now you might be wondering, why do the words contradict what we just found? And in fact, if we look at the picture, the graph, why does the graph contradict what we just found? Well, it's because we made a very common mistake, and it's one that I wanted to make here to highlight how easy it is to forget something and then get the complete wrong answer. And what we forgot was the constant, right? The second derivative, f double prime, was equal to negative 8 over x to the 4/3 times 6 minus x to the 5/3. And I've seen this happen to a lot of students. They get so fixated on the two factors, right, that actually have zeros, that they forget that there really is a third factor here, a negative 8. It's just a factor that doesn't have an x in it. And so when we were calculating our actual pluses and minuses for the entire function, we had to remember that there was a negative 8 here as a factor, which meant that there was always going to be a negative piece added. And so the function itself as a whole would have been negative, negative, and positive. And now we see concave down, and then concave up, which matches what is written up here and the graph. Okay, so just be careful. Don't forget those constant factors also have a bearing on both of the tests, the second derivative test and the first derivative test, because they're both all about signs, positives and negatives. Okay, and also don't forget that 6 here is an inflection point, but 0 isn't, because by the definition, an inflection point is where the function changes concavity, and the function doesn't change concavity here. 0 is just some of these, it's a corner point, right? Some of these weird things where the function has a sharp corner, sharp turn on it. Okay, and that's everything we need to know with first and second derivative tests and how they relate to the graph of a function.